Hello and welcome to another video. In this video we're going to be doing leaf similar trees, and in the problem you have leaves of a binary tree from left to right, and the values of the leaves form a leaf value sequence. So in this example here we have 6, 7, 4, 9, 8. So you go left to right for all the leaves. And you're given two trees and you are asked to determine if the two leaf value sequences are the same. So in this first example we have 6, 7, 4, 9, 8, and here we have 6, 7, 4, 9, 8. And all the other nodes don't matter, and like the number of nodes doesn't have to be equal. So even though there are 4 and 4, you can have whatever nodes in here, count doesn't matter and values don't matter. So basically all these nodes, doesn't really matter how many there are and what the values are. And in the second example, they are not the same. So here we have 2, 3, and here we have 3, 2. So to demonstrate this, we have two trees. Like I said, the nodes that are not leaf nodes don't matter at all, the values and how many there are. So I just marked them all with X's. And here is our leaf value path, right? So in this one, it's 1, 2, 3, 4, 5. And in this one, it is also 1, 2, 3, 4, 5. So these should return the same thing. And it's a little bit tricky to figure out how to do this, right? Because basically, how do we traverse this and actually get the leaf value path here? But it's not too bad, right? So we basically need to traverse this tree and get this path 1, 2, 3, 4, 5. And we need to traverse this tree and get this path 1, 2, 3, 4, 5. So essentially what we can do, and the other thing is we kind of want to traverse it in order because you want to get all these numbers, but you want to get them in the right order. So for example, you want to visit 1, then 2. So let's get rid of this. You want to visit 1, then 2, then 3, then 4, then 5. Not only do you need to get the values, you need to get them in the right order. And how do I do that? Regardless of your trees, right? Your trees can look whatever. The number of nodes here doesn't matter. So just because there's 6 and 6, this doesn't have to be like this, right? Like for example, we can get rid of all of this, let's say. Like this would be reasonable. So let's say, obviously this arrow is off. Let's just take this one, copy it, disaster. Okay, there we go. So let's say we have something like this. And let's put that here. And there we go. So even though like these trees look completely different, let's make this green. Even though these trees look completely different, okay, well, that's fine. This should be the same thing, right? It's still 1, 2, 3, 4, 5. So basically, how do we do this, right? How do we get the path here and the path here, and we have to visit the nodes in order? So it turns out you can actually do like a pretty basic traversal. So if you just start at a node, and let's go for this tree first, and you just go left and then right all the time, you're going to actually get these values in order. And let's demonstrate this. So let's have our visited like things. So we're just going to go left and then we're going to go right and then like recurse back up, right? So it's just going to be like a basic recursion. So we're going to go left, and here we're going to go left, and here we're going to go left. So we found a value, 1, so we're going to record that in. Then we will recurse back up. There is no right value, so we will recurse back up. Then we will go right. Then there is no left value, so we can't go left, so we will go right. So we're going to record 2. And then we will recurse back up, recurse back up, recurse back up. Now go right, now go left. And we have 3. This doesn't have any values, so recurse back up, go right, then go left, 4. And then recurse back up, go up, and get this value here. So that's the left side. Now let's do the same thing for the right side. So literally, while we're at a node, we're just going to say recurse left and then recurse right. So let's do it for this one, just like a basic traversal. I think this would be like, because we don't really care about the root node, you can't really say if it's like in order or post order or whatever. But basically, we are just going, we're always going left and then we're going right. So let's do that again here. So we're going to go left, go left, go left. Get a 1, recurse back, go right, get a 2, recurse back, and recurse back. And then we're going to go right, go left, get a 3, recurse back up, go right, 4, recurse back up, recurse back up, recurse back up, and go right, and 5. And we're just going to have 2 arrays of values, and then we just can check, are the values the same? And if they are, then this is true, and if they're not, it's false. So no matter what the structure of your tree is, if you simply just have a recursive function, call it like fn or something, and your recursive function just says go left and go right. And we're going to recurse, and every time we hit a leaf node, we will just write it into our array. So I'm just going to make a helper function, and I will pass in an array, and we're just going to be writing into this array. That way we can just call that function twice on 2 empty arrays, and those 2 empty arrays should give you the same value. So let's code that up. So we're going to have 2 empty arrays, so we'll just call this like result1 and result2. And we're going to make a helper function, so just a normal traverse function as I normally make for trees. It's just going to take a node and the array that we're writing into, so we can call this like result or something. And so what are our cases? So if the node is null, let's just return. And then the other case is we have to check if it's a leaf node, right? So if not node.left and not node.right, then this is a leaf node, so we want to write it into the array and then return. So we can just say result.append node.val and then return. Otherwise, if it's not a leaf node, like I said, we just recurse left, recurse right. So we're going to call traverse node.left and result and traverse node.right and result. Now we can just call this function twice on result1 and result2, and this function will write our values into these 2 arrays. So we can say traverse root1 with result1 and traverse root2 with result2. So now root1 or result1 will have the leaf nodes in order of the root1, and traverse2 will have the leaf nodes in order of result2. Now we just have to check both of those. So in Python, to check 2 arrays for equality, you can actually just do this. This should be root. This should be result1. So if you do double equals on 2 arrays, it will check the values instead of like a lot of languages. If you do this, it will check if they are actually the same array. So I think for like JavaScript, this would be false. But in Python, this checks the values. This doesn't check if they're like in the same place in memory. So depending on your language, either do something like this or just go value by value and make sure they're the same and make sure the lengths are the same. But in Python, you can just do this. So let's run that and submit it. And there we go. So pretty good. And it's like, yeah. I think there are some optimizations you can make to not have these 2 arrays to actually compare the values. But because worst case runtime is going to be of like each tree, it's not going to make it significantly faster, and it'll be a lot tougher. So this is going to be pretty good. So let's talk about the runtime here. So let's call tree 1 root 1, and let's call tree 2, or let's call root 1 n, and let's call root 2 m. So basically, just like a normal traversal, you're traversing every node of both trees. So this will just be n plus m. Yeah, and the space. So for the left one, there's the recursive stack space, which is O of n, right? Like that's always a thing for trees. Like let's say your trees are just something like this as always. You're basically just going to recurse down every single node here. So this will be O of the length of the tree. So that's O of n. As far as the number of leaf nodes, it's going to be roughly half of n, right? Like worst case scenario, because if your tree is like perfectly, like let's take a look at this example. If we have something like this, right, just like a perfectly complete tree. So here we have 8 leaf nodes and we have 7 non-leaf nodes. So that's always going to be the case. In a complete tree, you're going to have roughly half of, I think it's like whatever the non-leaf nodes are plus 1. So roughly half of it is going to be leaf nodes. So that's also O of n. So worst case scenario, basically of O of n here, and worst case scenario of O of m here. So this is just going to be n plus m because we're storing both. You could alternatively write more code if you want to only store one of them, which would be kind of straightforward. So let's say you could store like one of these, and then you can just traverse the other one, and every time you check a leaf node, just check like, is it the same one? Or like I said, if you want to make the super complicated one, you don't need any of these 2 arrays. You can just have a function that will keep checking, like it will just traverse both trees, and every time you get to a leaf node for one tree, get to the next leaf node for the other tree and so on. But that's more complicated. I think this is pretty straightforward, and the runtime is like the O complexity is exactly the same for this, and that one. So we're going to go with this one. So if this was helpful for you, and if you like this problem, and if you like this explanation, then please like the channel or like the video and subscribe to the channel as always. And I'll see you in the next one. So thanks for watching.